In this series of videos I'm attempting to repair this Toshiba Toscal BC1411 calculator. It's a Nixie tube calculator, as you can see. It's fairly old. It was designed back in the late 1960s, so it's a real vintage piece of equipment, and this particular one has several faults, or at least one fault that may be manifesting itself in several different ways. In the previous videos in this series I stripped the unit down, took the boards out, and I worked my way through the backplane and connectors and cleaned them up, and tried to make sure there weren't any obvious breaks in the connections, and I then looked at the power supply. Now it's quite difficult trying to explain the general process that I use for working on something like this, and unfortunately, while it's not very useful advice, really comes down to experience and having worked on many pieces of equipment like this, because there is no easy approach to doing this. But having said that, they are a huge amount of fun to work on. Something like this is very discreet in its design. So this one's DTL, it's diode transistor logic, very discreet. There's no central processor, and it's got a very unusual memory system. So it uses a form of dynamic RAM, which actually uses discrete capacitors rather than DRAM chips, which obviously didn't exist when this unit was designed. When this was designed, there was a whole range of memory systems being tested and tried and prototyped, and this is a particularly interesting one, so it makes this machine quite interesting to work on. I don't think there's a fault with the memory. There could be, but we'll get back to that later. Now, the first thing I want to look at is to see if the power supply is behaving itself. In the previous video I had the power supply on the bench and I was testing it separately, and the voltages seemed to be okay, but I did say in that video that the supply doesn't really regulate the voltages as such. It kind of uses a divider system with some pots that you can adjust to set the supply voltages. Three main voltages on this: plus 10, minus 10, and around plus 200 for the Nixie tubes. So what we'll do first is, as you can see, I've refitted all the boards, and the reason I've done that is I want to see if with the correct loads on the supply it's giving us the correct voltage. I also want to see if we've still got the same fault, although I did find some fairly dodgy looking connections on the backplane. I don't really think that's what the fault is in this. The fault is too consistent. When you get faulty or poor connections on backplanes and you move things around, you'll tend to get a kind of moving target, and the fault will change in its character. This fault seems very fixed, or it did before I dismantled the unit. So we'll power this back up, make sure I haven't actually broken it, and see if it's still doing the same thing, or maybe we have actually fixed it. So we'll get it powered up. Seems to be doing the same thing, so 9 plus 3 is 12, that's correct. And if you recall, that was the only function that worked. Plus was the only function that would function. So we'll try to multiply. So it has changed. I don't know if you can see this. When I press multiply, the display does change, but then it locks up until you clear. So clearly that is not working. We'll try subtraction. That clearly is not working. And we'll try dividing. And as you can see, that's not working either. So the only thing that's working is the addition. I'll go briefly through fundamentally how a system like this or unit like this works, and getting an understanding of the general system you're trying to fix when you're working on something like this is probably the most important step in getting it working. But it's not necessarily as obvious as it might seem. Notice I've got one board in the risers. We'll get back to that later. I kind of assumed this wasn't going to work still, so I've put a particular board in the risers, and I'll explain why I picked that board in a few minutes. But the first thing I want to do is check the supply voltages. I suspect they're okay, because if they weren't, then addition wouldn't work. but we'll check it anyway. What we'll do is just open the keyboard. It's on the hinge, so it makes it quite easy to work on. We'll get the multimeter in, hopefully you can see that. And what I'm going to do now is just test the supply voltages. So as before, I'm going to test it relative to ground. So at 9.5 volts, that seems fine. Minus 9.5 volts, so that's fine. That's well within an acceptable range as to what we would expect it to operate over. So that looks fine. So in the previous video I also said that the minus supply will draw significantly more current than the positive supply. I'll explain a bit more why that's the case in a few minutes, but before I do that we'll just actually check this. So I'm just going to lower the camera so you can see the current meter. Okay, well hopefully you can see that. It's kind of saying 0, and it's not 0, it's a few milliamps. That's on the positive supply. If we now look at the negative supply, which is on this blue wire, so hopefully you can see that. We're drawing almost exactly 1 amp. So the minus supply is drawing significantly more current than the plus supply, but it is about the right range we were expecting to see. So around 1 amp on the minus supply, around it's going to be 10 or 15 milliamps on the positive supply. I'll just quickly explain why that is before we proceed. So what I've done here is sketch out a typical DTL circuit. Normally when you see the circuits from machines like this, they're drawn the other way up, so to speak, with the negative rail at the top and the positive rail at the bottom. But just to make it a bit clearer as to how this is organised, because it's far more typical these days to have the positive rail at the top, and if you're not used to seeing it the other way up, it can look a bit confusing. But essentially it uses PNP transistors. And this is a flip-flop. It's typical DTL circuit that you'll find in something like this calculator, and there'll be many of these circuits or something similar in this particular calculator. I'm not saying this exact circuit will be in there, but this is fairly typical of the time. And what you'll see here is that the positive rail is only being used to give some base bias current for the transistors, and that's just a few microamps. It doesn't need to be very much. And the main current that we get is from the 0 volt rail down through the transistors to the minus rail, and that's the main current path that we get with a DTL circuit like this. And there are thousands of components in this machine and hundreds of transistors, each of which is significantly adding to the current draw. It's only a milliamp or two, but you add all those together and it is fairly significant. But just a few microamps, even 1,000 times, is only a few milliamps. So that's why the negative rail typically will draw much more current in a device like this. And this leads us now on to how to go about trying to repair a piece of equipment like this. What you will have noticed if you look at the back of the boards is that we have what appears to be many duplications of similar circuits. And again, that's not surprising. It's a digital system, so it just really comprises of lots of circuits like this that are used to store information. And the general operation of this calculator is based on a state machine. So when you're repairing a system like this, trying to figure out exactly what it is you're expecting to see can greatly simplify the overall repair process. So that's really the approach I generally try and take, is I try to figure out what I'm expecting to see. Now, to start with, these calculators will operate in a very similar way to a mechanical calculator. It's just an electronic implementation of a very similar system. It's kind of the natural progression of development back then. And so That's the approach I would take with this, and I know that this particular calculator uses a hardwired state machine for its general operations. That gives us a lot of clues as to how it's going to work. Once you've figured out the overall operation, then even the faults that are present can give you some clues as to where to start looking. So what I'm expecting to see in this particular design is a state machine. If you're not familiar with a state machine, then it's really just a sequence controller. If you've read my book on the transistor processor, then the state machine in this calculator would be the same type of thing as the instruction decoder and control matrix in the processor. So it's really just a series of hardwired circuits that generate a sequence of events and allow you to perform certain, sometimes very complex system behavior, and what appears to be a programmable system where really it's not. It's just a series of cleverly worked out sequences. So what we're expecting to see, there'll be a clock to drive everything. That will generate a series of pulses, of course, and we'll then need a series of, we'll call them phase generator signals, but they may all actually be in the same phase, but we'll call them phase signals just to make things a bit easier. I don't know how many there will be, I haven't looked at this system yet, but in general what we would have is something like this. So as we run through each cycle of the machine, then we have a pulse that occurs at a particular part through the cycle. I would then expect to see a series of control latches, and that would be something like this circuit. It's basically a flip-flop that you would enable or set, and they would be set based on the particular function key that you press. So for example, there would be one maybe for addition, one for subtraction, one for multiplication, and division, all the functions that the system can create. What we then need is a series of circuits that do the actual work, and how these are organized will depend on the particular architecture of the machine. But there might be one for moving data from register A to B, one for adding two together, subtracting, that sort of thing. I don't know what they are yet, I haven't looked into this, but for each one we would need a control gate on its input, and this is so that we can determine if and when it's going to be needed. So as an example, we might hit the plus key, and that might enable two of the circuits. This is just an example. So it might enable these two circuits, and the first circuit might be activated on the first phase of the system, and this one may be activated on phase 3. So as the state machine progresses, we hit the plus key, it enables these two. Neither one does anything straight away, but this one will be operational when the first phase pulse occurs, and then this one will be operational when the second phase pulse occurs. But of course we have more than one function, so let's say we now hit the minus key, and in this case it wants to make active this same first function. Well, it can't do it directly because these will be obviously shorted together. So what it does instead is there are a series of diodes that are used to isolate which particular function operates at any given time. And we have the same thing on the phase signals. So the phase signal for this one, for example, might be sequenced and used multiple times, and we can isolate its operation by including diodes. And the same with this can obviously feed more than one circuit by having some steering diodes. And what this allows us to do is select a particular function by setting a flip-flop, similar to our circuit that we've just looked at. That will enable one gate or more in the system, depending on what the function is that we're using. So a complex function like multiplication, for example, might well use all of them. And we have something like this. And then the particular phase that's used will depend on the requirement of the system to carry out its particular role. Doesn't go there. And so we have diodes to steer the signals. So the way this operates is the clock runs the phase generator. We hit a key to select a particular function. That sets a flip-flop. That will enable the various function steps or function circuits that are required for that particular function to operate. And then as the phase signals progress through the cycle, it will in turn operate whichever circuits in turn are required to fulfill the overall operation of the system. So what we're looking for to start with in our fault finding process is a clock generator, the phase generation circuits, and then the control diode matrix somewhere that controls the operation of each of the circuits. Once we've found this section, what we can do is start following the individual lines through to see where they go, and then we can identify the individual control circuits, see what they're supposed to do, and then we can backtrack these from, for example, addition, see which ones are being used for addition, see which ones are used for subtraction, multiplication, and then see which ones are working and which ones aren't. And then we can individually identify the blocks of circuits to see what each one is supposed to do. And because we have an idea as to the nature of the fault that we're looking at, it will give us some clues as to where to start looking. The first thing to do is find the clock, make sure all the phase signals are working, because if one of these is not working, then you might find that addition will work because it doesn't need a particular phase, doesn't do anything, whereas the other functions might need that phase to work. So it's a way for us to narrow things down. So what we'll do is we'll get the machine back on the bench, get the scope out, and we'll start trying to hunt out this particular block of code or block of circuits and see if it's working. Okay, so I've got the scope connected, and again, be careful when you're working on a machine like this. Make sure you understand what is ground and what isn't. It would be very easy to either blow up the machine you're working on or your scope if you're not careful. But I've got the scope connected to ground reference on the calculator, and the reason I selected this particular board to put into the riser is because the designers were nice enough to give us some pointers on this. And up here, I don't know if you can see it, but in the copper trace it says OSC, probably short for oscillator. There are other symbols on here, and there is text on some of the boards that might give us some clues later on as to what we're looking for. But this is almost certainly our main oscillator, and this down the right hand side I believe is going to be our phase generation circuits. Looking at these are just kind of flip-flops, so it looks like this block of there's 2 transistors in each, and it looks like that is this sequence or series, which means that this big block of diodes is almost certainly this, which is what we're expecting to see. This is what I was saying, like trying to figure out what we're looking for, and it will make identifying it very much easier. So I'll get it powered up and start probing around, and what we're looking for is a clock signal. Now I believe this only runs at 30 or 40 kilohertz, so we're looking for a 30 or 40 kilohertz square wave signal, and I believe it'll be somewhere around here. We know the clock's running because first it clears itself when you turn it on, but also the addition function worked, which it wouldn't if the clock was not running. But like I said, it doesn't mean that all the phase signals are working. So I'll get it powered up. Okay, so no smoke, so I've got it connected to the right point. I'll try and keep my hands out of the way. And what I'm looking for here, so this looks like an Ace-double DTL multivibrator, so the output should be on one of these two diodes. Oh, there we go. Lucky first guess, and that's 38 kilohertz, so that is clearly our main clock, and I would suspect, quite hard to get this without getting in the way, that each of these is one of the phase generation circuits. So that's these, and the outputs should be going through to the diode control matrix, which is this. And if we look at the tracks on the board, we can see that from each of these there is indeed a trace going across to the common connection bus. So these diodes, the one end of each block, are common, all connected together, and I suspect the other ends are going off to the various functions in the machine. Indeed, we are getting a signal. Try the next one down, and the next one, and the next one. So you can see that the relative timing is different, so that's what we were expecting to see. I'm showing it here as different phases, but it looks like they all are triggered at the same time but have different time constants, so it's probably the falling edge that's actually doing the work on these. And if we keep looking through, we can see that all the signals are pretty much exactly what we'd expect. So we're getting a narrow pulse on the top one, and then gradually winding pulses as we work our way down. So I'm pretty certain these are the phase pulses. So what I'll be doing is making sure that each of these circuits is behaving itself, and these go across to these blocks of diodes, and so the outputs of these will be really repetitions of whichever particular signal is required for a particular function. So now we know what the function of this little circuit here is. We've got a good idea now as to what this block here is, and this is really the starting point, this bank of diodes, for further fault finding. Now I suspect this block of diodes here has something to do with the control of the various functions within the calculator. So I'm just going to clip the scope probe onto one of these connections. It doesn't really matter which one, I'm just trying to find somewhere to do this without destroying anything. Okay, so I've got the scope probe hooked onto what looks like to one of the output rails. So these diodes are all feeding into these traces that we can see going down to the edge connector, and because we've got multiple diodes going to each of the various traces, I'm suspecting it's this type of arrangement where we've got kind of a control matrix of diodes all feeding common output lines, in which case that means that these traces we can see are really the control lines going to the various functions in the rest of the machine. So I'll now try hitting a key, and if we're correct, then we should see some activity only when we hit the key. So then it will stop once the function's complete. So I'll try hitting a key, try and stay out of the way of the scope. And sure enough, if I hit another key, or the same key again, it doesn't repeat. So try the plus. Okay, so that's interesting. It's So the first time I hit the key, in this case I was hitting the multiplication key, we see the signal, and it does not repeat unless I hit the clear key. So in other words, the state machine seemed to be getting stuck somewhere, and that's kind of what we expected. It's trying to go through the state machine process and it's failing, and this is a very good way for us to proceed now. We can follow one of these through, see where it's going, try and figure out the general sequence. We know how the addition works in a general calculator. We know what multiplication is. We know that the addition works, but multiplication doesn't, and because the multiplication is most likely repeated additions, then we know that somewhere in the control matrix we should hunt out the addition function by following through what happens when we hit the plus key, and then see if that same block of code, or rather block of circuit, is triggered when we hit multiply, and then we can follow it through and start trying to figure out what the various blocks are. Sorry if this all sounds very kind of convoluted and confusing. It is the nature of these machines, and unfortunately, like I said, it's very difficult trying to explain the general process in fault finding something like this, because it's going to change every time I touch one of the points with the scope probe, and my thinking changes as to exactly where I am in the process. But the first thing is to identify what in general is going on in the machine, and for me this card was the starting point, because I'm fairly certain, based on the general appearance, that we have the phase generator, the phase control matrix of diodes, and then the function control matrix of diodes over here, and that's the starting point for our fault finding process. So next thing to do, next video, we'll start following these various lines through, see where they go, and the easy way of doing this is we can just turn the unit on its side or its back and see where the physical connections go, and then we can figure out what each of the cards is doing. There is also some further text on some of the other cards. So what we'll be looking for is some control flip-flops that will be used to control the state of the state machine. The phase of the state machine is most likely controlled from here, and then we can work our way through and try and figure out which part of that state machine is failing.